Welcome back to the System Design series. In the previous video, we learned about the 8 activities that make up the system design methodology, and in this video, we will learn how each of those activities relate to the various software models that we have also learned earlier. Likewise, the design choices we make during certain activities can influence the choices that we would have to make in other activities as well. But before we do that, let's do a quick recap of the various type of models and the system design activities so that we can refresh our memory. If you remember, a functional model describes the functionality of system from the user's point of view. The function model can be represented via a use case diagram using UML. We created the use case diagram for our concert app. We learned this provided us with the high-level view of the functions that we need to support for our system. Then we moved on to learn the object model. The object model describes the structure of the system in terms of the objects, their attributes, the associations, and the operations that can be performed on the object itself. And then we use the class diagram to represent the object model for our subsystem. As an example, we build the class diagram for a sample concert app where we identify the various classes like the user, the ticket, the event, and define the properties and functions for each of these classes. Finally, we represented the association between these classes. This diagram provided us with a high-level understanding of the components and the relationship within a system. We worked on building the dynamic model, which describes the internal behavior of our system. The dynamic model outlined how objects in a system collaborate with each other to accomplish the various use cases. In case of dynamic model, we use both the sequence and the state diagram to represent the dynamic model for our subsystem. We created a sequence diagram for our use case, the purchase ticket, which showed the interaction and the collaboration between the various participating objects for that use case. Then we learned how to build a state diagram for our entity, the ticket. The state diagram showed us the illustration of all the states the ticket can go through as well as the transition between these states. So this effectively helped us understand the state diagram for a given object. Similarly, let's do a quick recap of the 8 system design steps. Identify design goals. The first step is to identify the design goals using the functional and the non-functional requirements. System decomposition. The next step involves decomposing a larger system into various smaller subsystems. Identify concurrency. We look deep into our dynamic model and find opportunities for parallel execution. This specifically is important for any large-scale system. Hardware-software mapping. In this step, we focus on picking up the right hardware and software that is required to support our system. Persistent data management. This is a very important step, especially for large-scale system where we have to identify the right database for a system and subsystems. Global resource handling. In the next step, we deal with security and access management concerns to make sure that a system is secure and all the required access controls are in place. Software control. This step helps us to identify how the information flows in our system. Should a system be centralized, decentralized, and so on. Boundary conditions. Finally, once all other activities are done, we focus on the last step, that is to handle the boundary conditions. These boundary conditions represent use cases like initialization, termination, and failure of our components within our system. As we move from analysis to design, at a high level, let's find out how does these various software models like the functional, object, and the dynamic model will influence or help us with these 8 system design activities. Likewise, I already mentioned before that the design choices that we make in certain activities will have an influence on the later activities as well. From the non-functional requirements, we identify our system design goals. Remember, the non-functional requirements help us to capture the qualities of the system and act as a constraint on the functional requirements. Functional model. As we work with our stakeholders and understand the requirements, we define our functional model. We use this functional model to help us break down our system into various subsystems. Likewise, we use it to figure out the boundary conditions as well. For example, in a concept app, we can break down a subsystem into various services like the event service, ticket service, payment service that will help us accomplish our use cases like search events, purchase tickets, etc. Further, we identify how does one service impact other service, and this helps us design fallback solutions for the boundary conditions. Object model. Based on the object model we have defined for our system, now we can define what all objects need to be stored and what is the best database that we should use to store and retrieve our objects as well. For example, we can use an RDBM system to store our entities like the users, events, and tickets. The data can be stored in separate table with foreign keys linking each other. In a similar way, we have defined association between those objects. Also, the object model can influence the hardware and software mapping activities. For example, if we have to store an image or a video associated with an object, we would have to choose a blob storage solution like the Amazon S3. Dynamic model. The dynamic model outlines the services and the interfaces. Using the dynamic model, we can identify how we can support parallel execution and handle concurrency. For example, in our concept app, we have to make sure that the same ticket does not get sold to more than one user. For the global resource handling, we have to make sure that the artist can only manage the events that they have created. This will require us to design role and permission-based access policies. Software control is another area that can be influenced. Should we choose event-driven architecture that reacts and takes action based on the current state of the ticket event? Event-driven architecture enables increased resilience because it reduces the dependencies between the applications. If a particular service fails, we can restart the service, recover events, and then even replay them if needed. Hardware and software mapping. Lastly, depending on the type of the hardware and software we choose, it can affect our boundary conditions. For example, if we choose to deploy a service to a data center instead of a cloud, how will we handle those failures and recover from such services, and how will it affect our design? What if we deploy to the cloud? How will that affect our design as well? As you see, in both cases, we need to account for the impact, but the way we handle the impact may be different. Another example, if we choose a caching system like Redis, we have to account for what happens when the server crashes. Do we need a backup? Or how can we switch from the existing backup that we have? The takeaway from all of this is that any such activities, whether it's a system decomposition, persistent data management, and so on, and the models that we create to represent the various aspects of our system, both aid each other and also can influence each other. As a system designer is to make sure that we understand those influences and adjust our design in such a way that we can still meet the overall requirement and the design goals that we started with.